Okay, so we've done quite a bit of practice on confidence intervals. We're going to go ahead and do some work on significance tests with the exact same type of process. We're dealing with a difference of proportion. Okay, and remember that we use confidence intervals to prove specifics, like to prove that our test came out correctly. And we will be using some of the confidence intervals, the data from it, to run significance tests to see, so that we can go back and look at our confidence interval and show that it does actually prove whether or not you got your inference test right. Okay, so you're going to have your HOHA. And this is very similar to when we were doing the mean of a difference, only we're actually going to write it out as two separate pieces. Then we just did mu equals 0 because we normally assume that there's no difference. And then we did either it doesn't equal 0 or it was greater than 0, less than 0. Well, when we're talking about the difference in two proportions, we actually have to write it out. Okay? And when we do our state and we actually define our variables, we actually have to state what P1 and P2 is. We don't have to state what order we're subtracting anymore because, it's very, very obvious from the way we've written it. But we do have to state what P1 and P2 is, okay? Or you could make one big statement, which we'll actually practice that one as well, where you could say that P1 minus P2 is the true difference in proportion between, and then you state which way you're subtracting. So you can either define them separately, and it's very obvious they're being subtracted, or you can define it as one whole statement. But we will get into that. Okay, so we are still doing our statistic minus parameter divided by our standard deviation of the statistic. So that hasn't changed. That parameter, being the mean of our difference of proportions, basically. Same thing we've been doing. The standard deviation of the statistic is that same big square root with one difference. Okay, this is not on your formula sheet, and this is something that you need to study because it changes your standard deviation just a little. Okay, if you've been reading the chapter like you're supposed to be, as far as for section 10.1, there's something in there specifically about it. Okay, so for an inference test. Okay, normally when we're doing, and when I say normally, I'm like 99 times out of 100, we're going to state the difference between the two proportions is assumed to be 0, right? And then we're going to try and prove with our alternative that it's either not 0 or greater than 0, less than 0, whatever it is, okay? This changes our standard deviation just a little bit. Instead of doing the two separate pieces and putting them inside the square root, right? We're not interested in them being separate because we're assuming, right, that there's no difference between them. That's what that null hypothesis means. Okay, so we combine the pieces. We combine the successes and the sample sizes, okay, for both. And we use something that's called PC, right? P hat C. Okay, this is the only test where this is used. All right, we don't do this for the difference of means. We didn't do it for the mean of a difference because we were only using one piece. And we don't do it, this is the only weird part, we don't do it for a confidence interval for a difference of proportions. Okay, only specifically for a inference test on the difference of two proportions. And it basically means that you're going to have the same thing twice up underneath your square root because you are combining them. You're going to add your two successes and add your two sample sizes, and then you're just going to get one basic decimal from that. Okay? And it only affects the standard deviation, so please do yourself a favor. Put a note, put a star, put a box, put a highlight, something. This is specifically for only for the difference of proportion and only on the standard deviation of it. Okay, not for anything else. Okay, so that's what our formula looks like now. And again, it's the same exact formula. Now, for those of you who like using the stat tests in the calculator, it's still an inference test on the difference in two proportions using a z distribution. I'll write it out. It's the same exact thing. And your calculator automatically does this. It will automatically combine the two pieces because you're going to give it both counts of successes and both sample sizes. If you were doing your difference in proportions, your confidence interval in there, you'll see that in the calculator. It does ask you for both. Okay? And there's nothing wrong with using the calculator to do the test. You just have to make sure that you're writing out on your do part what the actual test is. Okay? So all of that just to get through the fact that the standard deviation is just a tad bit different. We're going to work it out, by hand on the first one, and we'll do some practice on this. So, no stress. Okay. And again, we already know how to do an inference test. We've already been doing that. So at this point, this is just showing the steps and doing the work. Okay? So, they're comparing the proportion of children who come to school without eating breakfast at two different elementary schools. Okay? So there's basically what would end up being in your conclusion and what in your state as far as regurgitating back at them the question they're asking. All right, so then we have N1, and then we have N2, all right? Okay, and then we have P1, because that's the first one, and then we have P2. Okay, so we have all the information that we need, and the part that gives it away, as far as it being an inference test, is the statement about is there evidence, and evidence is proved through an inference test. Okay, so you have this. Let's go ahead and actually start setting it up. All right, so state. Okay, and again, remember that we assume that there is no difference between them. So you say P1 minus P2 equals 0. Okay, and then well, it says difference. It does not give a direction as far as one school having more that don't eat breakfast. So at that point, because it is just a difference that we're looking for, we don't care about the direction. Okay, and this is where I'm going to put both possible definitions of your variables, right? I'll put both of them up here, and you can decide which one you like the best. Okay, so the first one being, okay, P1 is the true proportion of students who don't eat breakfast at school 1. Okay, and that means that obviously that P2 would be the true proportion of students who don't eat breakfast at school 2. Okay, so that's defining them separately and letting your statement, your null and your alternative, speak for which way you're defining it, or which way you're subtracting it. Okay, if you want to put them together into one statement, you are allowed, but you need to make sure that you are actually stating which way you're subtracting. Very, very important. Okay, so you could say that P1 minus P2 is the true difference in proportion of students who don't eat breakfast at school 1 minus school 2. Okay, and again, the choice is yours. Now, please note that when we are doing our conclusion, what we are going to state is going to be in terms of the true difference in proportion of the students. Okay? So the choice is yours on how you want to define it. Me personally, like I said, I would probably go with this because that is how we're going to state our conclusion as well. Okay, but the choice is yours. You can define them separately. All right, plan. Plan hasn't changed. It's still random, independent, normal. And the independence is 2 different times 10s, and the normal is all 4. So random. Yep, SRS given, so we're good on that. Okay, independent. There are more than, let's see, 80 times 10 and 150 times 10. Students at school 1 and 150 times 10 at school 2. Okay, normal. We're going to have to check all 4 of them. Making sure I have enough room. All right, so going to have to check all 4, successes and failures. So from the first one, 19 out of 80. Okay, so for our normal, 19 is greater than or equal to 10. And then 80 minus 19 would be 61, greater than or equal to 10. Okay, that's at school 1. And then at school 2, 26 out of 150. So 26 greater than or equal to 10. That should be 124 greater than or equal to 10. And that's just for me, school 2. And I'm going to state that that is my success and that is my failure. Okay, so we are approximately normal. So we're good. Greater than 10 successes and failures for each one. Okay, the do. Let me see if I can squeeze it in and get it all to fit. That's the fun part. Okay, so somewhere off to the side, I'm going to go ahead and grab my iPad again to get my Desmos. Go ahead and off to the side, combine your successes with your sample sizes, please. That's going to be 19 out of 80 plus 26 out of 150. And we need to get our combined, so for our standard deviation. Okay, so again, I'm going to do this using nothing but Desmos. So I should be able to actually figure this out, hopefully. 19 out of 80 plus 26 out of 150. Okay, so my combined decimal is going to be, we're just going to call that 0.41. Okay, and then we do actually need the 19 out of 80 and the 26 out of 150 individually, at least for the statistic in the front. So 19 out of 80, since that is school 1, and that's the way we're subtracting, is 0.24. Okay, and then 26 out of 150 is 0.17, so minus 0.17. Okay, so that's your statistic, minus your parameter. The parameter is 0, right? That's what we said in the null. Okay, divided by It's going to be this really big square root, but the good news is all the numbers are going to be the same. So it's going to be 0.41 times 0.59. Let me pause this for just a second to show you. Okay. See, the sample sizes don't change, just the probability of success and failure. Okay, so I want to make sure you caught that. Okay, so out of our first sample size, which is 80, and then 0.41 times 0.59 all over 150. Okay, and again, this is one big, long square root. And there's nothing wrong with doing this in parts, just to make sure that you don't screw up, trying to put it all in at once. And I'm going to go ahead and put in the square root, and you be putting in the square root, and we'll make sure we come up with the same answer. Times 0.59 all over 80. Okay. I'm getting 0.068 for my standard deviation, which is nice. And then 0.24 minus 0.17 would be 0.07, 0.07 divided by 0.068. All right, so whatever that is, that's going to be my z-score that I have to then go look up. It's going to be pretty close to 1. All right, so I'm getting 1.03 because of the rounding. So we have to go look up that z-score. Okay. Let's see, where are we at? Nope, I want the table. Where's the table? Nope, that's not it. Let's see. Does this have the table? No. Oh, no. Can't find my Z table. Let's see. Ah, here we go. Okay, so positive 1.03. You're probably ahead of me at this point. 0.8485. Now, hang on just a minute, because we talked about this last chapter when we were doing significance tests. Okay, this is a not equal to. Therefore, it is two-sided. Okay, so really what we're supposed to do is we're supposed to look at the negative version of that. Since it's two-sided, right? We go look up negative 1.03, and then we double whatever that is. So negative 1.03 is 0.1515 times 2 is going to equal 0.3030. Okay, that is our actual p-value, right? That's the probability given this z-score. Okay, so you look up the negative version of it, whatever it is, and then you actually just double it. Now, let's just say you get a negative 1 and you're doing a double-sided. You're fine. Just look it up and double it. But you should always look up the negative version, because that is the smaller version. That's the part that would be leaving off like that little bit down here, because it would match whatever little bit was up here, the two-sided. This would give me the positive value. If I look that up, I mean, I could subtract that from 1, I'd get the same thing, but it's easier just to look up the negative version of it instead and double that, okay, because that would be what you're leaving off, being that it's two-sided, okay, and we did do that when we were working through those last chapter. Okay, so now our conclusion based on our p-value. That is greater than, well, whatever alpha reasonably that you would pick, because this wasn't stated, so you got to pick your own, right? It just says, does it provide evidence? If we do alpha equaling 0.05, that would be fine. We could also do alpha equaling 0.10 or 0.01 if you wanted to. Okay, so we are going to fail to reject, right? And this is where some of you kept getting backwards, even on your open response last chapter. If I am failing to reject, it's because I do not have enough evidence to support the alternative. If I reject, it's because I do have enough evidence. And it's always in terms of the alternative. To conclude that, okay, and this is where we go back up to that alternative or the definition of your hypotheses that I was talking about. We do not have enough evidence to conclude that the true difference in proportion of children who do not eat breakfast so because it's stated as that the alternative is it's not 0, we don't have enough evidence to conclude that the true difference in proportion of children who do not eat breakfast is not 0. Now, if something is not 0, that means there's an actual difference between them, right? I've seen people phrase it that way, and they didn't get dinged. They basically, we do not have enough evidence to conclude that there is a difference in the true proportion, and I've actually seen them phrase it that way because, if something is not equal to 0, that actually means there is a difference. So just be real careful. Think about what it is that you're saying. We don't have enough evidence to state to be able to prove this. Okay, that is what we're trying to prove, that there is somehow a difference between the proportion of kids in each school that don't eat breakfast. Okay, so and that was what we have failed to prove. Okay, so going back and what I was talking about with a confidence interval, right? If we were to run a confidence interval for this same data, which again, you already know how to do in your calculator, we've already done it, you would put in the number of successes and the sample sizes and it would do it for you. What you're going to notice is 0 is, if I'm failing to reject, that means 0 is in the interval. Okay, that means that my interval is going to go from a negative to a positive number. Okay, and since 0 is in the interval, that proves that 0, them having no difference, or the difference between them being 0, is plausible, basically, is what you're saying. That it is possible for this to happen if the confidence interval contains 0. Okay, and we're going to be putting all that together before you take your test in this chapter, because I want you to start backing up your inference tests with just a really quick confidence interval. You've already got the data and all the numbers. You just throw it in the calculator. It's not like you have to do another state plan to conclude. You just give an interval to back it up. A couple of you have already been doing this. I know for a fact Allie has, so if anybody wants to ask her questions on how she does it with the extra step to make sure, it's a good idea. Practice it, because that's what I'm going to have y'all start doing. Okay, so we're going to do one more for today, and then I'm going to give you one to work on. Okay, so let's work through this one real quick, make this a very short one. So let's see, males or female students more likely to attend college outside their home state. Okay, so that's what they're asking. So is there evidence, there's your keyword, that it's a ho-ha, to suggest that there is a difference, which means all they care about is the not equal to, in the proportion of males and females, so that's the way we're going to subtract, that attend college outside of Texas. Now, why are they giving us this whole big table if all we care about is this column? Well, because if you add those two together, then you have your sample size and you have your successes and your failures right there. This is a really common thing to do difference of proportion questions like this. Instead of giving you an SRS or whatever it is that and telling you what the total is, they just give it to you in a table, okay? And they tell you to just run the test. Okay, so let's go ahead and write our HOHA. All right, so, and it's very basic, P1 minus P2 equals 0. And it's the same thing again. P1 minus P2 doesn't equal 0 because we don't care about direction. We just care about a difference. And then, P1 minus P2 is the true difference in proportion for male minus female students that attend college outside Texas. You could put in the true difference in proportion for Texas students that attend college outside Texas, and then you put male minus female afterwards. That's also fine. Again, getting those key points in there. All right, so plan, random sample given. It does actually say that they took a random sample. Okay, we're going to have to do a little bit of adding here to get our actual independence. So independence, 121 plus 329 would be 450. Okay, so there are more than 450 females times 10. Females. And yeah, college bounds. Okay, so high school seniors basically. Okay, and then we need to add the 94 and the 212, and that's going to be 306. Okay, so there are more than 306 times 10 males, high school seniors, and you can put in Texas because really that's where they're at. And then again, just your list of successes and failures, right? 121 greater than or equal to 10. What was it? 329 greater than or equal to 10. And then 94 and 212. 94 greater than or equal to 10. 212 greater than or equal to 10. Okay, and that's your successes and your failures. And it's approximately normal. And you could label them, these are their women and these are the men, or males and females, your choice. Okay, so do. Go ahead and combine, again, your totals and your sample sizes, or your success rates rather. So 121 plus 94, so off to the side, plus 94 divided by 450 plus 306. So go ahead and do that. All right, so 21 plus 94. Okay, that's 215 out of 756. Divided by, 756. Okay, that's 0.28. So we have our statistic. And then we need our separate ones, right? 121 out of 450. Okay, and that's going to be 0.27. Oh, wait, no, males minus females, right? Yep, male minus female. Okay, so the 0.27 is going to go in the back side. so minus 0.27. All right, so the males was 94 out of 306. And that's 0.31. Okay, and that's going to be minus 0 because, again, that's our assumed mean. And then our big, okay, so 0.28. What is that going to be? 72 over 450. And 28 and 72 over 306. So go ahead and put that in your calculator and get that figured out. Again, I'm just going to sit here typing on my iPad in my Desmos. Pause the video if you want to keep going. Oh, huh. Oops. That's not 0.16. Silly me. That's 0.04. That's why that was so big. That would definitely make a difference. Okay, that makes much more sense. All right, and remember that we're going to go look up the negative 1.21 for our z-score. Negative 1.21 is 0.1131 times 2. Okay, so that's our p-value, 0.2262, and that is greater than alpha of anything reasonable. Okay, again. So, and then our conclusion, we fail to reject the null. We do not have enough evidence to conclude. Now let's come up with another way to state this. We do not have enough evidence to conclude what? Well, I'm subtracting males minus females, and I don't have enough evidence to state that the difference between them is something other than 0. So let's think about what that means. That means, now granted, no, we never accept the null, we never accept the hoe, but if I'm failing to reject, I don't have enough evidence to say that the null isn't true. So we do not have enough evidence to conclude that actually, you know what? That the true difference in proportion of males minus females going to school outside of Texas and proportion of males minus females going to school outside of Texas is anything other than 0. We can say that because that's exactly what that means. Okay, so I'm going to give you one to do. Hang on for just a minute because I had it sitting up here and I have to go find it again. But I believe it is, oh, wow, what year was it? Was it 2004? Well, I guess we're going on a trip together. So 2004. Nope. Yep, here we go. I think it was 2004. It's either 2004 or 2006. See, they want you to even answer a survey here just to help them out. All right, so 2004. Okay. Nope, not an experiment. I know that one. Nope, that's not that one. Huh, maybe it was 2006 then. Okay, so we're going on an adventure in our video. Nope. Nope. No, that's a mean. Nope. I may have to just send it out to y'all. Okay. Thought I had it. Fun. But, okay, so we're going to do more of these tomorrow. You're going to do one for yourself. You'll do another one for yourself tomorrow. And then we're going to start talking about inference when you're doing an experiment, which changes just the conclusion, actually, the way this is stated and the way oh boy, the way the variables are defined, because we can't talk about population when we do an experiment. That's cause and effect only. Okay, so I'm going to send it to you. I'll just go ahead and send it out and remind, and I'll do that now and schedule it to go out tomorrow. But yeah, we'll do at least one more of these tomorrow as far as an inference test, and we'll do it with a confidence interval at the end, and then you'll do one, and then that's Wednesday. No, this is Wednesday. So that would be Thursday for y'all, and then Friday we'll start on inference for testing for a proportion, and then next week we'll do means. So your test should probably be sometime around the end of next week. Okay, so holler at y'all later.